Okay, it's time to start doing some actual calculations. So look at this problem. Calculate the total mass of a cube of side length 2, centered in the origin, whose mass density is given by rho m, which is a function of x, y, and z. Okay? So first let's picture this cube. So this is a cube of side length 2, which means that, for example, this is 2. Yeah, so it's 2 by 2 by 2. And it's centered in the origin, which means that the center of this cube is at the origin. So if we add now the axis here, the axis would be entering the cube here in the middle of these faces. So this would be x, y, and z. Yeah, and they would join at the center of the cube. Okay, so that's our cube, which means that what are the limits in x, y, and z? So clearly the limits are -1 to 1 in all of the directions, x, y, and z, right? Because it is centered in the origin, but it has a side length of 2. And now we also know that the density is a function of x, y, z, and is given by 1 plus x, y squared, z squared in kilogram per meter cubed. So that's the density. So let's calculate the mass of this cube. So the mass of this cube is equal to the triple integral of dm in the volume V, which is equal to the triple integral of, what's dm? It's the mass of a little mini cube. So that's equal to the density, which is 1 plus x, y squared, z squared, multiplied times the differential volume. Okay? So that's how you would do it. So let's apply Fubini's theorem. So we turn this into an iterated integral. So it's the integral between -1 and 1 of the integral between -1 and 1 of the integral between -1 and 1 of this equation here with respect to x, then with respect to y, and then with respect to z. For example, I chose the order arbitrarily. Okay? This is an iterated integral, and it would be actually quite long to calculate. So instead we can find a shortcut. So how can we find a shortcut? Well, first of all, we can say that this triple integral is actually a sum, right? So we have 1 plus x, y squared, z squared dv. So therefore we can split this integral. So integrals, the same as one-dimensional integrals, multiple integrals are linear. So if we have a sum inside of the parentheses, we can write this as a sum of integrals. So this is the integral of 1 dv plus the triple integral of x, y squared, z squared dv. Okay? Now the integral of 1 dv is really easy because this is just the volume of the cube, right? And the volume of the cube is 2 cubed. Okay? So it's 8. That is the result of that integral. While the result of this integral, notice that now the integrand here is a product of 3 functions which depend only on x, only on y, and only on z. And therefore we can apply separation of the integration. You remember there was a video about that. So this means that we can do the 3 separate integrals and multiply them all one times the other. So this would be the integral from -1 to 1 of x dx times the integral from -1 to 1 of y squared dy times the integral of -1 to 1 of z squared dz. Okay? And this is actually really easy to do. For instance, this first integral is x squared divided by 2 between -1 and 1. And actually we don't need to calculate any further because this is equal to 1/2 minus 1/2, which is 0. So this goes to 0, and therefore this second term will be 0 because it's 0 times something. So we can stop there And we can say that the final result is equal to 8 kilograms. Okay, which was this first term here, because that term disappeared. So you see that we calculated the mass of the cube, and I just really wanted to highlight this problem because you should always look for shortcuts. You could have done this iterated integral, okay, that would have worked. You have to integrate this with respect to x, substitute the limits, then the resulting function, you do the integral with respect to y, substitute the limits, and then the resulting function, you do the integral with respect to z and substitute the limits, okay? And you would have gotten the same result, 8, okay? But now let's move on to part B, which is focused on the same cube with the same density, but part B asks, calculate the center of mass of this cube, okay? So the center of mass now is a three-dimensional vector, which is given by three components: the x component of the center of mass, the y component of the center of mass, and the z component of the center of mass. And although I haven't explicitly told you how to calculate centers of mass for using triple integrals, by analogy with single and double integrals, you can guess that the center of mass is simply the weighted average of the position vector weighted by the density, okay? Which means we do triple integral of the position vector r multiplied by the density, which is rho dv, and then we divide by the triple integral of the weights, which are the density, rho dv, okay? Now remember that this notation of having a vector inside an integral just means that we can do the integral for each component and the result will be a vector, which is what we want because we want the three elements, x, y, and z, okay? Or to be more explicit, you can write this. Let me move this a little bit to the side. We can write this as the triple integral of the position vector, which is a vector that is x. So position vector is this vector, x, y, and z, okay? Or if we write it in terms of the basis vectors, this is x times x hat plus y times y hat plus z times z hat. Okay, that's r vector times rho dv divided by the triple integral of rho dv. Okay, so this is basically equal to three integrals. So this is x hat times the triple integral of x times rho dv divided by triple integral of rho dv plus y hat times the triple integral of y rho dv divided by the triple integral of rho dv plus z hat times the triple integral of z rho dv divided by the triple integral of rho dv. Okay, I basically applied linearity to split this integral into three, yeah, and then I took the basis vectors outside of the integration because they are constant. Okay, so you end up with these three components of the vector, where of course this component is the x position of the center of mass, this component is the y position of the center of mass, and this component is the z position of the center of mass, because this is our vector x center of mass, y center of mass, z center of mass, which is our vector r center of mass. Okay, notice that we are now playing with vectors. You know everything about vectors by now, so you know that a vector can be written as basis vectors times the components. Yeah, so this component will correspond to the first component here. So we can calculate this, of course. So instead of calculating the three terms, let me show you how to calculate the first one. But of course, the other two, you have the solution in the notes, so you can go. But let's calculate only the first component of the center of mass. So x center of mass is equal to the triple integral of x times rho d rho divided by the triple integral of rho d rho. So let's substitute. This is x, and now rho is equal to this function here, 1 plus xy squared z squared dv, and then the bottom integral is the triple integral of rho dv, which we solved in part A, is equal to 8. Okay, so we can always keep a 1/8 on the beginning. Okay, so now what I'm going to do is I'm going to expand this. So this is 1/8 triple integral of x plus x squared y squared z squared dv. Okay, so I left the 1/8 outside and I just multiplied the brackets out. And now I can integrate this using a similar trick that I did in part A. So I can divide it into two integrals because we are adding two terms. And the second term, we can split it into three using the concept of separation of integrals. Okay, so let's do it. This will be equal to 1/8 times the integral of x dv plus the integral of x squared y squared z squared dv. So let's write the limits exactly. So this will be equal to 1/8 times. So this triple integral, which has limits -1 to 1, -1 to 1, -1 to 1, and where dv is equal to dx, dy, dz, yeah, it is separable because x is equal to x times 1 times 1. So this is a function of x, this is a function of y, and this is a function of z, right? You can say that. And therefore we can apply separation of integrals. So this first integral will be the product of three integrals. Integral of -1 to 1 x dx times integral -1 to 1 of dy with a 1 implicit here, yeah? So I don't have to write a 1 here, but I could do it if I want. And the integral of -1 to 1 of dz. So that's the first integral, plus the second integral, which I can also apply separation of integrals because this is a function of x times a function of y times a function of z. Therefore, I can apply separation. So -1 to 1 of x squared dx times integral -1 to 1 of y squared dy times integral of -1 to 1 of z squared dz. And now I can solve these integrals separately. So this first integral will be x squared over 2 evaluated between -1 and 1, and as before we don't need to continue because this is 0. So all this term will go to 0, and therefore this whole term will be 0. And then this term here, so the integral of x squared, that's 1/3 of x cubed between 1 and -1. The integral of y squared will be 1/3 of y cubed between 1 and -1. And this term will be 1/3 of z cubed between 1 and -1. So actually the three terms will be identical. So what is each of these terms? This is equal to 1/3 times 1 cubed minus 1/3 times -1 cubed, which is -1, so plus 1/3, which is equal to 2/3. Okay, so this will also be equal to 2/3, and this will also be equal to 2/3. And therefore the final answer is 1/8 multiplied times 0 plus 2/3 times 2/3 times 2/3, which is simply, if we do this calculation, 8/27. And that is the final answer for the center of mass in the x direction. So this is the x coordinate of the center of mass. Okay? So you can repeat the same for the other two components. Simply instead of x here, we will have to write y or z. Okay? I made everything very slowly because I was clearly specifying each step, because this is one of your first integrals ever. But you can see that once you get fast at this, you will immediately notice that maybe I could directly write from this. I would directly write this, probably. You don't need to go through the intermediate steps. And also you will quickly notice when something is 0, so you can cancel out the entire terms, and so on. Okay, so practice, practice, practice. As usual in maths, you have to do lots of problems. Thanks for watching, and see you in the next video.